In this part 2 out of 2 video, we will show a couple of more examples of rigid versus flexible analysis in S Foundation. As you will remember, in the first part video, we saw an introduction to rigid versus flexible analysis code checks and one example, a spread footing with a thin white slab subjected to a big compressive load. In this part 2, we will see a second example, an isolated footing with smaller, thicker pad plus a large lateral load. And example number 3 will be pretty similar, taking into account some slight changes to the lateral loading. Let's start with example number 2. We have the dimensions 3 by 3 by 0.8 of the pad, pedestal, as you can see 0.5, 0.5 by 1, and a compressive and lateral load, as you can see in this image here. The assumptions we are taking, we will ignore the self-weight of the concrete and soil, and since this geometry was chosen specifically to illustrate these concepts, and it is not representative of an actual foundation design, we are not concerned about the reinforcement checks, and we will ignore the rebar. Now let me open S Foundation. So I open a new model in S Foundation, and I start defining my isolated footing for example number 2. So the parameters of the pad, this is a 3000 millimeters by 3000 millimeters, and the thickness is 800. And for the pedestal, I just need to change one of the sides to be 500. So 500 by 500 by 1000 of height. I'm not going to include any base plates, even though this is not relevant, and I can place my foundation. Now, the demands we're applying, I just need to define a new load case, a compressive force of 600, negative z direction, and a lateral load of 500 kilonewtons, and I will apply it here. For this case, I will run every code check, the rigid and the flexible, and we will perform a nonlinear static analysis. So we should expect that the model will experience significant overturning forces, and these forces may compromise its stability. We chose to use the Skyline solver in the design input, final element analysis option for this analysis. The solver will produce more detailed diagnostic messages to describe the instability that we are expecting and attempt to prevent some rigid body motion using small springs in the system stiffness matrix. So with these changes, I just stick to the concrete code I have, CSA, go to run, analyze. It's going to ask me to save my model. I just give it a name and save. And as we can see, we are receiving some messages right away saying the moment is causing eccentricities to be too large for the pad. That's fine. I'm expecting this message. It's also mentioning that some of the checks were not able to be performed. Click OK. And if I expand this window, in the design output window, where I can see the different code checks that are failing, it is evident that all the failing code checks, but one, is from the rigid analysis method. So the loss of contact is the only one flexible that is failing. We also notice some utilization ratios showing infinity. The difference, once again, is due to the methods that we use to characterize the pad's stiffness, the rigid versus flexible analysis. Despite this pad thickness, the large overturning forces that comes from the lateral load can show us the pad will exhibit slight flexibility. And this can also be seen if we use the soil bearing pressure tool. And remember to select the flexible method. Basically, the bearing pressure result should not be a huge surprise. We have a massive load going in the lateral X direction, and even with that, it's showing like 10% of the pad still in contact with the soil, and showing the pressure here. So everything that is showing in color gray is not in contact with the soil. If we use the rigid, we can see that we're getting the unexpected results. Soil bearing pressure of 0 kPa, and this is because the software assumes the pad is 100% rigid, and this will cause instabilities, of course, and cause this foundation to overturn. S Foundation will not run other rigid code checks that rely on the underlying bearing pressure when no bearing pressure exists. It will appear that for this scenario, the rigid analysis approach is not practical, but its foundation leaves this decision to the user. You can always go to the design input, so I'm just going to turn off all these checks and run once again. It's going to ask me to save my model. Now the rigid checks are not accounted for, but I still see some failures, loss of contact. Now this example is an extreme case handpicked for this illustration, and we ignore other real-world design considerations. Our focus here is only to illustrate the differences between each approach, the flexible and rigid. Now let's consider a slightly different case scenario. For example number 3, we have the same dimensions for pad and pedestal, same compressive load, but there's a slight change in the lateral load from 500 to 300 kilonewtons. And we will take into consideration the same assumptions. For this case, we will only perform the rigid checks. And here is the same model I used before. Let me just go to the design input window. I'm just gonna activate this rigid check just to show you something. And the only difference we have here, if I go to the reaction tool, I'm just gonna apply slightly different lateral load and click here to apply it. Now I'm able to run an analysis and code check. In this case, nothing is of surprise to us right now, but I just want to focus the attention in the soil bearing pressure. If we see the flexible method, it will show us that a portion of the pad has zero soil pressure, and the maximum pressure happening at this edge is about 218 kPa. Now, if we look at the rigid code check, this assumes a linear pressure distribution under the pad. Just the far end of this pad is having zero pressure, and the pressure varies linearly until it gets to a maximum of 222, which is pretty close to the value of the flexible approach. The flexible method utilizes the underlying finite element model and nonlinear compression only springs to represent the actual interaction with the soil. And the rigid method uses the simplifying assumptions, which is consistent with the hand calculations that you may get from this exercise to represent the past rigidity and linear soil pressure distribution. It is worth mentioning that this example can be also found in S Foundation's help system. If you go to the help menu, you select online tutorials and videos, and you will be able to see the rigid versus flexible analysis method.